All right, we'll just go ahead and give people a chance to get settled. You know, while we're waiting for people to get settled, anyone here play the game Stardew Valley? Yeah, people like that game? How about Stellaris or any other 4X game? Yep. Skyrim. Anybody still playing Skyrim or no? Somebody is. So for those of you who really like games and really like a particular game, one fun thing that you might want to consider for a final project, and again, it's super early to start thinking about this, like really super early, but if you like video games and you like a particular one and don't necessarily want to write your own, but you want to do something, modding. Modding is a making a game mod is a perfectly valid choice for a final project. So whether it be just something to add more content to a particular game, or or adding new characters, adding a new dungeon, adding new options or a new system in there, all those things are valid. They're perfectly good ways. Plenty of people have gotten their start in getting involved in video games and video game company by doing mods for those. So mods are definitely a valid choice if you want to do that. And that's if you're interested in doing like something related to video games. The other thing that I have like very explicit advice about, if your interests are aligned there, is that if you are involved in music, so whether you've got a music major or minor, or you're in a concert ensemble, or you're doing marching band, if you're interested in music, you might want to take a look at algorithmic composing. In other words, this also applies, by the way, if you are interested in art and fine art or doing arts in general, right? Using computers to aid computational creativity. I'm sure you've all seen these days about like AI generated art or memes about AI generated art. Learning how that stuff works or being able to use it to create stuff, but especially using it to create something that is made by a human and by your hands, made by the computer's hands and your hands working together, is also really awesome. And I expect to see more of that. If you are not like, if you like music, by the way, and not really, and you want to make music, but you're not sure where to start, I can give you some pointers about that. I minored in music and took a lot of music technology stuff, and I am doing music composition is one of my side hobbies, so as well as my side research area. So primarily, if I do research, it's involved in computer science education. So, all right. So with that said, looks like people have gotten in there. Also, that Stardew Valley game is addictive. So, like, my wife just like really likes it, which is good because people are allowed to like games. Okay, so we're going to go ahead and again, I will probably be working this week and weekend now that my schedule is finally cleared with a bunch of stuff to work on the due dates for the semester. But for right now, we've got week 2. We've got week 2, part 2. And so now I'm going to go ahead and instructor's page, assignments. And I'll go through this and again put in the appropriate assignments. I've just been busy with other stuff this week that has completely imposed, making everything but the most immediate due dates. Week 2, part 2. And again, those quizzes, ignore those for right now because they don't actually exist. Again, I mean, since you're in here today, I'd want you to have it done by tonight, and we can find this by going to, so we can find this by going down and scrolling down to our third thing in our third project in our textbook, which is all a bit more abstract and less boring than turtles, but it's still very interesting, which is using computers as basically a very powerful calculator. That's one of the two things that this part focuses on. So we're going to learn how to basically really use this as a powerful calculator. But the other thing we're going to be working on today is figuring out how do you make like ballpark estimations there, because it can be quite difficult to like figure out these ballpark estimations. That used to be like like questions that Google would ask for interview questions. Turns out they're rubbish interview questions, but all right. So this lesson, we will use Python to do some calculations for us to solve some problems. So two important problem solving strategies, they say. The first is making and documenting some simplifying assumptions. We all make assumptions about our problems, but it's always good to kind of write them down explicitly, unless is that way if we are reminded that they are just assumptions. And the second is solving a problem by generalizing a simpler version of the same problem. So we've got this very standard, they talk about this very standard computing model that we use for our basically our first programs, which are like the first homework assignments, which are input, compute, output, which is basically as follows. Ask the user for an input, do a bunch of computation, give me an output. Okay. In fact, a lot of problems that you solve in computer science will be in this format. And a lot of times when we go and create functions, we will, as we get later in this course and create functions, we'll eventually drop the input part, and the input part is just going to be implied for when we actually call stuff. So this one is very much related to the homework for homework 2, right? Enter the number of years, and I'll tell you how many minutes that is. So let's take a look at how this works. So we're going to run it first, right? So so when you do an input box in Runestone, it will pop it up over here on idle. It will, the input will be in where the output normally is. So you'll be wanting to ask there. Enter a number of years. I'll tell you how many minutes that is. I put in 1 year, hit enter, and it tells me that it is 525,600 minutes, which somehow feels less than you'd think, right? Now, how does it get to that? Well, it does that by just breaking the problem down into multiple steps. So the first step over here is, here we take the input, and the input is whatever you enter is of type string, right? There's a couple different data types in Python. This is of type string. We take in a bunch of text, that's what a string is, and we store it in years, right? That equal sign means we store it in here. Line 2 is possibly the most, how to say, important, conceptually important, because it's conceptually foreign. It's years equals years, in years. Because it's like, you know, if I were to do something like this in math, where I would say, you know, x is equal to 5, and then I'd say, sorry, give me a second to scroll down. So if I were to say x is equal to 5, and then I do x is equal to x plus 1, in math, this is a what? You don't, it doesn't, it's invalid. It's basically, you just created a logical fallacy, a paradox of some kind. In computer science, though, this is not a fallacy at all. This makes complete sense, because this is an operator. This is an operator. It's an assignment operator. It's not determining equality. What we're doing over here says, take a 5, put it into a box labeled x. Then for this next line, what we're doing is that we are saying, take x, what's its value? It's 5. Add 1 to it, that's 6. Now we do all the order of operations before we do everything. In terms of orders of operation, equals has the lowest precedent. So we always do the equal sign last. So x plus 1, that is 6, because x is 5. And then we store that result in the box labeled x. So we put 6 in x. So now x's value would be 6. Remember, this equal sign is a lie. Right? That equal sign looks more like that, except that that's, you know, less than negative, which is not really useful here. In other programming languages, older programming languages like Ada, I think, or Pascal, can't remember which one, there was something that we call now the Walrus Operator, because it looks like a walrus with his, you know, walrus eyes and his tusks. Okay, and that was used for the assignment statement. It's still used today, actually, in the Google Go programming language, for some, like, to basically make a very simple assignment statement where Google does a bunch of the heavy lifting for you, because it's a typed language. So, but for most, but basically it just got eventually shortened to this and said, CS educators will take care of that. So remember, this is an operator. So here, what we're doing is that we're essentially updating the value. So that, now that looks weirder with numbers. Here, it kind of makes sense. What we're doing over here is that we're getting an input, which is text, storing it in years. And then this command int says, hey, whatever you toss into me, I'm going to give it, if it's made of numbers, I'm going to give you numbers. But if it's not numbers, I'm just going to crash your program. So long as that's made of numbers, it will turn the numbers into actual numbers that we can use. So if I put in the text 123, it will become 123. So, and then it stores that in years. It overwrites the previous value. We can see this actually, I think, with code lens, right? So here, it's on the first line. Code lens is super useful, by the way. First line says, hey, put in a number. I'll put in 12 years this time. Submit. Not do that. Oh, there it is. 12 years. So it says years is 12. Then I do the next step. And now notice it was kind of subtle there, but it removed the quotation marks because it's no longer a number. Then the next line says, hey, let's do year. We'll take that number and multiply it by 365. Because again, what was the original program? It's been a while since I mentioned that. It was to turn years into the number of minutes. So to turn years into the number of minutes, we got to convert that to, we'll convert that to days, which will convert to hours, which will convert to minutes. We'll go from one unit to another unit to another unit, right? Rather than trying to figure out what the exact ratio of years to numbers are, we'll just turn it into what we know. We know that years are made of 365 days. I'm pausing there because that's a lie. Years are not 365 days. They are, in fact, they are something close to 365.25, but not quite, because years are complicated. All right. Then what we do over here, so that tells us how many days are in a year. So we take that value, 12 times 365, and we store it in days, which becomes 4380. Then we do days times 24, right? There are 4380 days in 12 years. Multiplied by that, there are 24 hours in a day, so we can multiply that by 4, store the result in hours, and we'll get that it's 105,000 hours and change. And we know how many minutes are in an hour, so we'll multiply hours by 60. We multiply by 60 because they're 60, because if it was 1 hour, right, you'd multiply by that 60 to figure out how many minutes are in it. If there was 2 hours, you'd multiply that by 60 to find out there's 120 minutes in 2 hours. And then finally, we print it. We say print out the variable years is, then we say print out the string, then print out the variable minutes, and then print out the word minutes, which it does over here. Okay, this code lens is very valuable. All right. So now let's go ahead and do some very quick tries on this. The first step is go and I'll check, and I'll intervene between each of these steps to get you up to where you need to be. First step, we want to change the problem to print the number of seconds. That's our first task. Change this problem so that instead of printing out the number of minutes, it prints out the number of seconds in a year. Then what we're going to do is that we will change the above problem to go in the other direction. Given a number of seconds, how many years is that? And then enhance, typos in textbooks, they happen. Enhance part 2 so you can print the number of years, months, days, and minutes. All right. So go ahead and let's try changing this to make the number of seconds. You want to make it print out there, blank years is however many seconds it is. So I'll give you maybe 3 minutes to work on that. If it seems hard, you might be overthinking it. All right. So overall, what we're going to need to do to change this program, to change so that it prints out seconds, is obviously we'll need to want to change the text over here to print out seconds. If we're changing this to seconds, we'll probably want to have a variable called seconds that we're going to actually print out the seconds with, right? So now the non-obvious part is, how do we convert there? Well, we just continue the chain that we've been doing. We have days is equal to years times 365. Hours, there's 24 hours in a day. There's 60 minutes in an hour. And for seconds, assuming I can type, I learned that at some point, seconds is equal to, well, there's 60 seconds in a minute. The number of minutes times 60. So what we'll want to do for that is we will just simply do seconds is equal to minutes times 60. Then we'll ask, oh, let's cancel, because of course the prompt is saying it will tell me how many minutes it is, and I don't want to be a liar. Let's scroll, so change, enter a number of years, and I'll tell you how many seconds that is. So 1 year was like 525,000 minutes, but now it is, it is 1, 2, 3, 4, 5, 6. It is 31 million seconds, which again feels like not that many when you group them all together like that. Okay. Now this next part can be a bit tricky. Okay, which is we're going to change this to go the other direction. So I'm going to go ahead and I'm going to go ahead and comment these out because it'll be useful to maybe reference it. But what we're going to want to do is we're going to go from seconds to years. How many years is this equivalent to? So my hint here is that I'll get you started on this, right? So seconds is equal to input, right? And then we'll ask for how many seconds. I'll just be a bit more terse. Give me seconds. I give years back. Okay, there we go. Very terse. All right. So now remember, the first thing you need to do is you got to take your input and you got to convert it into a number. Okay. And then since we're going the other way, it doesn't really make sense to multiply, right? So I'll give you 5 minutes till 2:25 to work on that. And then I will come back and I will show you how to do it. And again, if you're frantically trying to copy this out all down, I will share the code after this one. And then after we do the next one. Goes into it. All right, do people want more time to work on this? Okay, cool. Give you a few more minutes. Hmm. 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 All right. So we descended from years to seconds in the previous part of the problem, and now we will ascend from seconds to years. So first thing we're going to do is, as I mentioned, we'll want to convert this to a number so we can actually use it. Int seconds. So then we have to convert the seconds to minutes. Is equal to, so there's 60 seconds in a minute. So we'll do is equal to seconds divided by 60. And honestly, don't quibble too much about which division you should use. Yes. No, if you want to turn it into a float, so ints are integers, like so ints represent integers, which are in math terms, numbers that are whole numbers, and they range from 0 to positive infinity, negative infinity, but they don't have any floating points in them. Floating point numbers account for everything else, which is all those numbers from positive infinity to negative infinity that have a floating point number in them. So we take that, and here, to get from seconds to minute, we know that a minute is made of 60 seconds. So we would take the seconds and divide by 60 to get to minutes. Similarly, we know an hour is made of 60 minutes. So minutes divided by 60. Over there, we know that a day is made of hours divided by, so sorry, days are made of 24 hours. So hours divided by 24 would give us the number of days. And now a year, years, not tiers, years are made of days divided by 365. So we would go ahead and now print that out. We have to actually print it out if we wanted to see any output. So print out seconds is and then years and now we go ahead and run it. So if I put in 600,000 seconds, then it will tell me that it is approximately 600,000 seconds. Okay, let's go ahead and uncomment this out so that we can have our things to make sure I didn't make a mistake somewhere. So let's go and we'll go ahead and run this so we can get years to seconds. So 2 years is, let's see, so 2 years was right in the millions, right? Minutes was the thousands. So 2 years, and give me the number of seconds. That's how many seconds were in 2 years, which was 63 million. Yeah, 63 million and 72,000 is 2.0 years. If I put in, let's go ahead and say 1 and now whatever. If I put in 60 million, 0, 0, 0, 0, 0, 0. Notice in chat. Yes, you could do it all in one line if you wanted to. There's nothing stopping you from doing that. And you'll get a floating point number, which is perfectly okay because I didn't specify whether it had to be a float or not. Okay, now enhance part 2 so that, but if we were to enhance part 2 so that we would do the number of years, months, days, and minutes, right? Seconds, how many years is that? How many months, how many days, how many minutes? That would actually take quite a bit of work. And it's very similar to your problem, the problem we would have to do, right? A minute is this many minutes into seconds. What we'd have to do is basically have to do this. We'd have to say, okay, there are so many minutes, but honestly, it would be what's left over. So we'd have to figure out, hey, how many years are there in here? We'd want to figure out how many years are in there, and then take what's left over to figure out how many days are left over, then take how many minutes are left over, figure out how many minutes are left over. And we could honestly just kind of, once we break it up like this, we could do, hey, days is equal to, years is equal to days, divided by 365. What does that give us? That gives us an integer. Okay, let me comment this out again. This gives us an integer. And then that gives us how much is left over. Sorry, and then how much would be left? So this gives us how many whole years there are in that many seconds, right? If I were to do 365. Oh, sorry, if I were to divide by 365, right? What's the difference between divide and normal divide? Did you go over that? Yes. Divide gives you the int value. Modulo gives you the remainder, which is the percentage sign. So what we would do over here is that, hey, this is how many years are in it. And then we could figure out, okay, days would be equal to, sorry, and then we could say, hey, this much is left over, is equal to, the leftover amount of years is equal to days let's see. Yep, days mod 365. And then using that amount left over, we could figure out, okay, how many days are there in that amount left over? Days in that amount left over would be equal to, let's see, so we have this many days left over. We'd have to convert to years and convert to hours. Divide by 24. Then we just basically keep using leftovers as kind of a placeholder variable to do this. This one I'm leaving to you as basically kind of, you know, a challenge, because also I test you on this in your assignment. But it follows essentially the same pattern. Now, this other part, the reason I'm doing so is because I want, you know, to save time here, because we've got two more problems I want to talk about. This other problem is a bit more interesting than that technical problem. So the writer says that this is a question a friend of his likes to use as an interview question, which I've said is like, used to be a popular one, but it's good for seeing if somebody knows knows about ballparking. How many trees are in the state of Washington? A lot. Yes, a lot. All right. It might seem like an impossible question to answer, but has anyone actually gone out and counted them all? No. But as he points out in the text, the point of this isn't getting an exact count. The idea is, are you going to get into the same order of magnitude or close to it? And what does your problem-solving process look like? What are the assumptions, right, that go into this? If you haven't read XKCD, it's a great comic, but Randall Munroe, the author of that, wrote a great kind of idea about like Google. And if all the digital data were to be stored on punch cards, how big would Google's data warehouse be? And as he points out, Google certainly has more data storage capacity than other organizations on Earth, but they don't tell you, they're very secretive about that. That's corporate information. So it would be hard to say for sure. There's only a handful of organizations who might plausibly have more storage capacity or even a larger server infrastructure. Here's the short list of people who might have more than Google. The NSA, which of course is the National Security Agency. But then they put in the NRO. What's the NRO? Sorry? No, of course not, because it was classified until the 90s. The National Reconnaissance Office. Satellites. General satellites, I should mention, because the next is NGIP, which would be the military, and their I believe that is the military and their geographic information, which is, let's see, not that one, NGIP. Getting that. Interesting. NGA.mil. Yep. National Geospatial Intelligence Agency. In other words, people who do the group that explicitly handles war maps and intelligence on war maps, the CIA, and then other groups and companies. Amazon, now again, this was written basically I think 10 years ago at this point. So Amazon, Facebook, and Microsoft might well have grown. In fact, Microsoft and Amazon both have huge amounts of servers these days. But instead of like trying to figure out by basically seeing like, going and asking them, they mentioned that they have data centers here and they have other data centers. And the way they figure that out is to basically look at their electricity consumption. We can't just sneak up to a data center and read the meter. Wait, actually, can we? Somebody should try that. Instead, we'll have to do some digging. They disclosed in 2010 that they consumed an average of 258 megawatts of power. So how many computers can they run? So what he does is like, okay, let's do some math here. That's about 215 watts per server. So they probably grown. So then he uses that to do ballpark math to come up with like, okay, they held 10 exabytes of storage, which is, well, you've got terabyte, and then you have petabyte, and then you have exabyte, and it's 10 of those, so it's a lot of data. And then so you put it all together, that's a lot of bytes. So let's see. So that's what is that? That's million, billion, trillion, quadrillion, quintillion. So that's, yeah, a punch card holds 80 of those. So divide that number by 80. There you go. So to scale, there you go, as to how many punch cards that would be. The NSA possibly has enough, but basically the best trick for locating secret Google facilities might be the one revealed by an ex-Googler on Reddit. The easiest way to find manned Google data centers is to ask taxi drivers and pizza delivery people. Because of course they know, because they would have to make deliveries to the people working there late at night. So now, as far as, so going back to this, how many trees are there in the state of Washington? So we're not talking about Washington, D.C. We're talking about the state of Washington, which is all the way in the west. Now, question is, how much? So first question we might want to ask is, like, how much of that land is covered by trees? Better question to ask might be, how much land is covered by forest? Let's take a gander at Google Maps. So, and then basically use kind of this process of figuring out how to kind of ballpark that. So like, yeah, to compute the answer, you'll have to make it some wild assumptions, some crazy guesses and estimations that come up. Hint, you might want to start looking at a satellite view of the state. You can also use that data card thing as inspiration, but try to see if you can't figure out kind of a guesstimate for how many trees are in the state of Washington. All right. So go ahead and please work with other people on this. Please speak with other people, the people next to you, or if you don't like the people next to you, then abandon them and go meet with other people. And I will go ahead and pull up the satellite view of Washington for all of you. And remember, there is no correct answer to this because nobody has ever gone out there and actually counted the literal number of trees. The program is useful at the top of the large number of calculations. You know, use a regular calculator, but it's good to problem solve. But how do you take this problem and break it up into multiple parts? Let me go ahead and annotate my screen. I have roughly outlined the state for you, very roughly. All right. Is anybody stuck on where to go with this one? All right. So for people who are stuck, about how much of that state is made of forest? Like about like 50%? Yeah, 50% seems like a good number. Plus it's easy to do the math, right? So I'd say about 50% of that is forest. So then I would kind of, so what question should you ask then? Yes. How many square miles in Washington? That's another good question to ask. How many square miles are in it? Wikipedia. Okay. And then as far as forests are concerned, what information would you care about forests? How many trees are in a forest? That's an excellent question to ask. And that should, and using that information, that should provide you with a way to get to an answer. Yeah. I'll give you all like 5 minutes to do, like until no, 2:55. And if you're stuck, just raise your hand and I'll come over to you. Right. So first things first, let's talk about the question I gotta ask is like, what do you know, some of them could have them right here beneath the on the bottom beneath the podium. But look up, let me get to it. If you down one of the feet, right by the left, sorry, the right arm, there's a plug literally right below the arm. Depending on the building, it can be in different places. Yes. All right. So does anybody want to talk about their about what number they got? Now, again, I don't really, and I say that like I care about the number. I actually don't care about your number. I care about your thought process. So I just want to know what because everybody's going to come up with a different variety of numbers. So the range you're going to get is going to vary between like somewhere in the high 100 millions to the billions. Yes. Right? Okay. And what was the answer you got? And it keeps go. So that seems a bit low. I'm wondering if it's because of the square foot converting. But the anyone else? Yes. Around 15 billion. That sounds about right. So how'd you get there? How'd you get there to 15 billion? Uh-huh. Oh, wow, you can really zoom in. That's kind of spooky. Uh-huh. That's a pretty nifty way of doing it. I wouldn't have thought about zooming into the lowest level and then counting that and multiplying it out. That makes sense. Yes. There you go. Eastern? How many square miles there were? Sound right. In the millions is a pretty good place to end up in this, in my opinion. But again, what matters more is the problem solving process. And definitely, hey, looking up what the people who really care about forests say, what is a forest and how many things are in a forest, is definitely a good way to figure out, you know, your average counts. The people who write those things about forestry generally care very much about forestry. Nobody goes into forestry to be famous. They go into it because they care about nature. So, the way I personally thought about doing it myself was very similar to all the other approaches, which is, again, we figure out how many square miles there are, convert that into acres, because acres is the fun way that we like to say use land to figure out land use. Figure out how many acres that is. Figure out how many forests there are. Sorry, how many. So assume that that half of this is forest. Multiply by how many trees on average per an acre, and then divide by 2. Well, already had the divide by 2. That's why you write it down in multiple parts anyway. But the point being is that once you figure that out, you can. It's fair. It's the math is straightforward once you figure out what your assumptions are, and coming up with the assumptions is a hard part because there's this understandable hesitance to be wrong. Nobody likes being wrong, and so we get hesitant as to making an assumption, but we can always go back and fix our assumptions after we grab information. So similar questions that exist are like how many how many houses, if you could fit houses into the Empire State Building, how many houses would it take to fill it up? We stacked if we stacked houses, how many does it take to fill up the Empire State Building? Or similarly, how much does the Empire State Building weigh? That's another one, which again reduces to figuring out how many houses that makes up and figuring out how much houses weigh. And it all again depends on your assumptions, right? I saw sources saying, hey, a forest is 40 trees per acre. You mentioned the Washington state regulations, and they would care about their state. So again, it also depends on where you're getting your sources from. So our final exercise is this one below, which is using some math to figure out a question of combinatorics. So I wouldn't suggest actually going and shaking people's hands right now because we're still in the middle of the pandemic, but how many handshakes would it take for everyone in your class to shake hands with everyone else? You should not shake hands with any person twice, and you don't shake your own hand, right? And since the secret to this is starting small, so if the class only had 2 people in it, how many handshakes would occur? Just 1. If there was, right, I'll go ahead and just simply write it out. 1 would give us 1. 2 people, if we had 2 people in the class, how many, sorry, 2 people would give us 1 handshake. How many would 3 people give us? We have 3 people, how many handshakes would occur? 2. Alice would shake hands with Bob. Bob would shake hands with Carla. And then Alice would shake hands with Carla as well. So it would be 3. Right? So 4, add Dan into them. So let's go ahead and start drawing this, right? We've got using pencil and paper or drawing in general is an underrated tool in programming. So we've got Alice, we've got Bob, that's 2 people, add 1, we've got 1. Carla, once we add her into the mix, we've got 3. add Dan to the mix now. We've got 1, 2, and 3 added to that, which brings it up to 6. 5 people would basically that. Let's go ahead and add Edgar to the mix. Edgar's got to shake hands with how many people now? So we've already figured out how many these 4 need. So we're adding Edgar to the mix. He needs to shake hands with how many people? 4. So our answer is 6, the previous answer, plus 4, which would bring us to 10. Any guesses as to what this one is? $15. The next one would be 21, by the way, and the next one after that would be let's see, 28 after that. Any guesses? It's a pattern. I'm good at patterns. I know my patterns. This is triangular numbers. Sorry? 4. 4 underscore in range. So what we see with this is that we get a is that once we add a person to the mix, right? What we're doing here, once we add our 7th person, he's got to shake hands with the previous 6. And once we add our 8th person, she's got to shake hands with the previous 7, which adds 7. So adding a 9th person would add 8 handshakes. Adding a 10th person would add 9 handshakes. This pattern is called the triangular number pattern. It's one you'll see in computer science way too often. Basically where basically it's counting the number of pairings there are. So the question, and it turns out, so the question is, can we turn this into some kind of like equation of some sort? I mean, I know the equation off the top of my head because, again, like I mentioned, it comes in computer science, and I teach this course, and I have to teach this number pattern every single year in 2 classes. So, but let's go ahead and see. We've got, or you could just simply go off the fact that I told you it's the triangular number pattern, and go and look on Wikipedia. Work smarter. So triangular numbers. Now, the reason they're called triangular numbers, right? That seems like a weird name for numbers, right? But it's the type of numbers you get when you pile them up on top of each other. So our first triangular number is 1. And then our second triangular number is 3, then 6, then 10, then 15, then 21. This is the same exact numbers we got, except it wasn't 1 to 1, 2 to 3, 3 to 6, 4 to 10. It was 0. It was 2 to 1, 3 to 3, right? It was off by 1, but it happens a lot in computer science. But still is the pattern. We're just starting from a different place. And it says it's given by this explicit, and what we get, there's a bunch of scary math here because it uses scary Greek symbols. That's what makes it scary. But the equation over here is n times n plus 1 over 2. So let's see how that plugs in. If there were 10 people, so 10 times 11 divided by 2. 10 times 11 divided by 2 would not be that, because 10 times 11 is 1100. 1100 divided by 2 is 55. Be the 11th number. So in our case, if we wanted to know how many handshakes it would take, it would be whatever this number is. It would be whatever the number is, n, n is equal to 10. So our handshakes is equal to, well, again, n times n plus 1 divided by 2. Print my answer. Again, assuming I can actually type. Handshakes would give us, oh right, yeah, I have all this. Go ahead and comment this out. See, even I make these kind of basic, standard mistakes. The only reason I know how to fix them is because I do that a lot. So this gives me 55, but 10 should be 45. So what it is should be n plus 1, because we need to go up to, because if we want to fit the equation, we add 1 to it to fit the pattern. N plus 1, what? N minus 1, right? Which comes out to being the same. So 45, 10 gives us 45 handshakes. So there's like, I think, let's say there's 130 people, I guess, today, maybe. Run. So it'd take about 83,085 handshakes. So 8,385 handshakes. Apparently numbers are hard today too. So using and identifying patterns are pretty good, pretty useful. It's a tough pattern to figure out, honestly. Not sure how you're supposed to necessarily figure it out, but the equation holds. Triangular numbers are cool because, again, we use pairs of this stuff all the time. But the idea for this entire project is we can see how we use this all as a big calculator. We can use Python as a big calculator. Now here for this one, it doesn't really care what your inputs are so long as you've run it. So if you run, so long as you run the programs and answer these poll questions, you will get credit for the problem for today's assignment. Again, a lot of these done in the textbook for the day are, a lot of our textbook exercises are done for credit. Now, for those of you who, now let me just take a couple minutes to talk about the current and upcoming homeworks, right? Which again, I'm going to try to make sure that I get all the due dates plugged in today. Okay. So once I go over the homeworks, we'll be able to get you out of class and on your merry way. So yeah, modules. So lab 2 and lab 3. Lab 2 is messy chocolate, right? Which you should have seen already, which takes an old basal metabolic rate. This is an old formula. So, which is why they have it, there's newer formulas that are out there, but there's an old formula for figuring out your basal metabolic rate. There's a debugging question. And today's exercises are relevant for the temperature and the seconds to hours question. Your next week's homework. So now again, I believe Monday is Labor Day, right? Which means there's no class, which means there's no lab. Which means that for those of you doing lab 3, who would be normally doing lab 3 on Monday, it will be next Monday. Please give me just a couple of seconds while you're packing up, okay? Because I want to talk about the upcoming homework. Our next homework goes over loops and turtles. All right, there's one wording on the front. Be sure you follow the instruction there. If you're writing a program that deals with turtles, do not, under any circumstances, name your file turtle.py. The reason that is explained in the video that I have. It's the most watched video on my YouTube channel, which is titled "The Most Common Intro to Programming in Python Error." Okay, but the end of the day is because it creates a circular import issue. Okay, and I explain it. First question is you draw the Olympic rings. Okay. Second question is basically recreate this figure, which is like a figure of a clock. Third question is write your initials using turtles. For Turtle Olympics and for initials, using the circle function and looking up how to use that might be a lot helpful, especially if you've got a curve in your initial. The next is making a function, or not so much a function, but a program that takes where you prompt the user for a number and you draw for some number n, and you draw an n-sided polygon. So if they give you 8, you draw an octagon. If they give you a 4, you draw a square. If they ask you for 100, you do your best to draw a megagon. Yes, this is all supposed to be done for lab 3, which is next week. No, this is all for mask, yes. No. Once we get to next week, I will be running under the assumption that the Monday labs will be coming after the Friday lab, but before the lecture. So our work week becomes Tuesday through Monday. So and I'll try to update all the labs accordingly. Yes. The triangle. Yeah, I'll hit the share code button. All right. See y'all. Give me one sec.